Right on the dot at 9 o'clock. Very nice. Thank you for making it this morning. I've seen Universal. I've seen Universal yesterday at 1 o'clock at night, so I'm impressed how everybody's here. I'm Cornel Bullens. I'm a senior PM in the Skype for Business, Teams product group. Old habits die hard. So the first and foremost question, where's Thomas? This is Thomas's session. Thomas Binder, for those that have seen his sessions, he is blessed to have a second child. So he is at home enjoying his second daughter with his wife, and he's super happy. And he's giving me the daunting task to talk about media flows. So it'll be a Dutch accent, not a German or an Austrian one this time, but we'll try to get through. So for today, I'm going to be talking about the challenge with media flows. We're going to talk a little bit about our solution to dealing with that. I'm going to show you a little bit of that, and I'm going to show you some call flows. So our session objectives and takeaway. I'd like to talk to you about media connectivity, hence the title. We'd like to show you how our endpoints find the optimal media path. How can we identify connectivity issues and possible future connectivity issues? And the three things that I want you to take away back home is traffic can be peer-to-peer between clients. That's what we prefer. So although Teams is a cloud-based service, the traffic itself will mostly traverse between the two peers. You should always leverage local internet breakouts. Talk a little bit about that during the presentation. But please, centralized internet breakouts are not conducive for a good Teams experience. And then please open port 3478 to 3481 UDP on your firewall. If you do those three things and you promise me you do them, you essentially get 45 minutes off, right? You can skip the session. So a little bit about me. I'm Cornel. I'm from the Netherlands. I live in Houten. Yes, my country looks exactly like that, only windmills and flowers and tulips and stuff like that. I live in Houten with my girlfriend and two cats. She doesn't like me putting pictures of her everywhere, so I just put pictures of the cats in their natural habitat, which is sleeping. And in my time off, I own a brewery, because beer is good, as we've all experienced yesterday in Orlando, in Universal Studios. I've been with Microsoft since 2012, and I'm a member of the Teams PG. With that, for today, I do want to talk about media connectivity scenarios. I want to talk about connectivity. I'm not going to talk about quality. We did that on Wednesday. And we'll be talking about Microsoft Teams. If you still have questions about Skype for Business, want to know how Skype for Business or OCS or LCS actually connects over the internet and does its media connectivity, it's different than Teams. And my colleague Thomas has been creating videos for almost 10 years about LCS and OCS and Skype for Business and media connectivity. So if you'd like to know more about that, go to Channel 9, search for him, and he'll be doing these kinds of sessions, but then aimed at prior technologies. So the 5 acronyms that we will be discussing today. A candidate, when we talk about a candidate, that is the combination of an IP address, the port, and the connectivity technology, so TCP or UDP. And that's the connection target or for a source or a target. We talk about ICE, which is an interactive connectivity establishment. That's the coupling protocol. So that's stun, turn, they're all part of ICE. Stun is simple traversal of UDP through NAT. It's how we get our candidates. We have turn, which is a technology that our relay servers use to actually get connectivity through NAT. And we have a relay. Those can be media relays or transport relays. Now that we're all into Teams, we are no longer using media relays. we're just using transport relays. And I'll talk a little bit about the differences later on. For so far, the two further notes that I do want to make before we continue. Yes, this will be level 400, so we have about 38 minutes left, and I'll go through a lot of stuff. I suffer from the fact that I'm not a native English speaker, so I do make up some words, and I'm rather a quick talker. So if you miss something, if something is unclear, come up to me after the session, and I'll be happy to go through these terms or whatever we discussed in a one-on-one. So what's our challenge? Why are we talking about media connectivity? So the challenge is that when we have Alice and Bob and they really want to make a phone call, they use Teams because that's the coolest technology. So what happens is they actually start signaling throughout the cloud through Office 365, and you get the nice green bar, which is a signaling. So far, so good, right? It's port 443, we can get to the cloud, everybody's happy. Now we need to do media. Still, everything's happy because Alice can see Bob. They even have line of sight in my picture. So yes, they can do a media channel. It's easy. But now we're going to complicate stuff because we've added NAT. We've added a simple router, either at home or at work. There are routers in between. So NAT, they're devices that can translate multiple internal IP address to one public-facing IP address. And now that we've added NAT, our IP address is obscured. So now I can no longer get a direct connectivity between the two. Well, that's a problem. I'm going to make it more complicated because Charlie's going to join the party. But Charlie is in his nice company, and he has a corporate firewall. So while Charlie can do port 443 signaling all as well, he can't do media to Alice because there's this silly firewall in the way, and we've got NAT. They still want to talk to each other. We've got Dan. Dan also joins the party. He's in the same building as Charlie is. Signaling, still not a problem. Talking to Charlie, not a problem. Him talking to Bob, to Alice, new problem. So how are we going to solve for this? So the three key challenges that we had was NAT. We have to translate those internal IP addresses to external ones so we can go out. But coming back in, it's usually NATs are usually not one-on-one. So I get translated to a port and IP combination on my NAT router. That's usually not transparent. So when I go out and the other device tries to send data back, it doesn't do that. It says that that's unsecure. We don't want that. So it's just going to drop the packet. So I can't get back from outside to inside. Well, that's kind of a challenge. What it does do very nicely is ensure I don't need 10,000 public IP addresses for 10,000 internal clients. So there are some advantages, and it helps with security. There are also some disadvantages because Alice would really like to make a call. Challenge 2, corporate firewalls. If you open up all the ports on the firewall so you can get connectivity, there's not much point in a firewall anymore. So what do we do with that? They sort of have the same effect in the end as NAT, although it's more aimed at, I want to ensure that only the specific traffic to the specific ports gets out or in. So how do we deal with those corporate firewalls? Final challenge, proxy servers. So keep saying it, proxy servers are bad. We don't like them for real-time media. The official Office 365 guidance is don't do it. Bypass proxy servers for all real-time media traffic, actually for all Teams traffic that's going to Office 365. If you go to a proxy server, all UDP traffic will be transformed, will be forced into TCP, which is not good for your quality. There's some additional security, filtering of traffic, filtering of requests. You can scan downloads, which would be awesome if Teams traffic wouldn't be all secured by default. So it's kind of, now it has to do like a man-in-the-middle attack, and it breaks stuff. So for example, it breaks the Outlook plugin. And if it's UDP, usually it'll block it, so it becomes TCP. So HTTP proxy servers, one of the challenges, we want to bypass them. Now, we know that's not always possible, so we've thought of some solutions. And what we've done is it's an established protocol, and we've implemented this using something called ICE, stun, and turn. So ICE is the overcoupling mechanism, and stun and turn are part of ICE. So what happens? So we've got a client. The client connects to Office 365 using signaling. The green bar is here. So we use the REST API via HTTPS, WebSocket. That's how we connect to our online services. Now media, that's a separate channel. We have audio, video, desktop sharing. They all use separate channels from signaling. So what we do, we can add a relay there. Because as we talked about Alice and Bob, and there's NAT between them, they can't talk directly to each other. So what does the relay do? What the relay does, that's the stun-turn server, it actually reflects the NAT addresses B and E. And why do we have two NAT addresses? Because we have UDP and TCP. So we need two reflective addresses, and we also have the ability to relay those packets on the stun and turn server. So I'll go a lot more in depth about how that works, but this is the general concept. To go around the fact that we can't go directly to Alice and Bob because there's something in the way, we add a relay server on the other end, on a place that we know you can reach. We put that in our data centers, and we tell you to open up those ports to us, and we know you can reach at least that server. So the ICE protocols, or the ICE mechanism, what it does, it actually helps with that candidate exchange, and it helps you determine the optimal media path. So let's take a look at how this works. So first of all, which components use ICE? So all the clients, the Teams client on your mobile, on your PC, on your Mac, they all use ICE. And the services components in the cloud use ICE. We can use this for audio, video, desktop sharing. We don't use this for file sharing or for signaling, because that's all 443 directly to the cloud. We don't need any relays for that. We can go there directly. Then we have the relay, which is our special little service in the cloud. It provides stun and turn. And the one thing that's very important here, it doesn't terminate media. So your media will only flow through a relay. It will never stop at a relay. Especially when you have some of the security discussions, they might say, oh, you can tap the relay. Well, there's no media flowing. There's no media stopping there. Anything that's stopping the media at the relay will break the media path. So there's no media stopping there. It's just a relay. Also, because it's just a relay, we can handle thousands and thousands of calls because it doesn't need to work really hard. It just needs a lot of bandwidth. Well, it's on our Azure network. Bandwidth we have. Strangely enough, it's not an ICE endpoint. And as an honor to Thomas's jokes, it's not even a soft ICE endpoint. He usually calls all the semi-ICE components soft ICE. I'm just going to keep it here. It's not even a soft ICE component because it doesn't do anything. It doesn't terminate any media, so it's not any part of ICE. The only thing it does, it hosts components for the ICE negotiation. So it hosts the components of stun and turn. So where do we start off with these relays? So we used to have media relays. In our LCS, OCS, Skype for Business days, we had those media relays. They were living on our, for example, on our conferencing service. There was an audio relay. So what's the progression there? Because why did we go to transport relays? Well, we built those media relays for on-premise. So there were some caveats with building that. They need to be very close to the pool, for example. So if you were hosted in a European data center, our media relay had to be in Europe, which is kind of annoying if you're in the US and your colleague is in the US because you're both visiting Ignite and you want to do a call and you need a relay. Now all the traffic goes back to Europe and here just because you're located in a European pool. Doesn't work in a cloud world. So what we've done is we've gone into transport relays, which are independent of our pools. And they actually use dynamic discovery via an anycast IP, so you always get to the closest transport relay. Caveat, this only works if you're using local internet breakouts. As soon as you use centralized internet breakouts, this is broken. You no longer get any advantage of this, and you might even get a disadvantage. Don't use centralized internet breakouts. We use the same UDP port for all workloads in the media relay. For transport relays, we actually have separate UDP ports per workload. And a nice thing about doing it that way is that in this cloud-centric world, if you want to do any QoS on your network, you can now do QoS based on target ports, because you know that audio is going to flow to 3478 UDP, and you know the IP range because we've told you. So that's the evolution of our relays. Media relay no longer used by teams. Actually, they were never used by teams. We only use the transport relays. So the properties of a transport relay, it's an anycast IP address. So theoretically, all of our transport relays in the world have the same IP address. As soon as our client connects to that IP address, it automatically connects to the closest one to them. There are some privacy boundaries. So we have the concept of sovereign tenants. In certain countries, there's a special version of Office 365 for that specific country due to regulations. Those people will never use a transport relay in a different country. It's their law that says you're not allowed to, so we're fully compliant with those laws. Any EU tenants, because of some of the EU laws, they will only use transport relays in the US or in the EU. And all the other tenants can use any transport relay that's close to them. One caveat, and by now you should have gotten the gist of the caveat. This will only work if you're using localized internet breakouts. So are we getting where I want you to go? Localized internet breakouts? One of the other, I thought let's make a little picture and let's make it a little bit clearer on how this works. So we have our Azure network. So the gray blob, that's our Azure network. That's, it's the second largest internet network in the world, because we're number 2. This is actually a globe encompassing network. So what this means is that we essentially have our own private dark fibers between any data center that we own in the world, and we have a peering, a connectivity to any service provider, unless they have like 3 computers. So what this does is that as soon as you leave your own private network and you go onto the public internet, it takes about 2 hops before you go onto the Azure network. The nice thing about that is that as soon as you want to go, let's say you have a mailbox in the EU and you need to get some stuff from the EU, but you're currently in the US, you don't have to rely on how your provider is getting to the EU. It's going to be us. You're going to be on our network very quickly. One other major advantage that has, because we own that network and we can essentially put stuff wherever we like, what we've done is we've placed a bunch of transport relays throughout the world. So in the example that I have here, we have transport relay on all the edges of our Azure network. So we have them in the EU, in APAC, in the US, in Germany, in New Zealand, and those are just some examples. They're all over the world. So when that client, the EU client 1 and 2, even if they're hosted in that US data center, or maybe they're hosted in the APAC data center, it doesn't matter. When they want to have a conversation and they need a transport relay because there's a firewall in between them, they will use the closest one to them. That's the beauty of transport relays. All right, see, really trying to make this as simple as possible. Discovery load distribution. So when you try to discover which transport relay is closest to you, you will do the 1 to nearest association. Essentially, there's a mechanism behind it. As soon as you try to reach that IP address, your provider will route it to the shortest path. It will use the shortest path to get to the closest transport relay. Each transport relay has the same IP address, and the Anycast IP address finds you the closest local transport relay. There's some equal cost multipath routing. It's a big word. We use that within the group of transport relays in each location to ensure that as soon as you're connecting to one, even though they can take loads and loads of data and they can handle loads of sessions, they will never get overloaded because they inform each other how busy they are. And if one of the transport relays is really busy at the location, the next one will pick up and they'll take themselves out of the equation, so they will no longer get new calls until they're freed up. So how does this look like in action? Looking at ICE, we've got 5 phases. The first one, when we sign in, we essentially request credentials. I'm going to show you the MRES, the Media Relay Authentication Service, the Transport Relay Authentication Provider. As you might have guessed, the Media Relay Authentication Service, Media Relay, no longer being used by Teams. I put it in here because we usually talk a lot about MRES credentials. They don't exist anymore because there is no Media Relay, so no MRES. Now they're called TRAP, or the Transport Relay Authentication Provider credentials. So during sign-in, we need credentials. And why do we need credentials? Because when we talk to that transport relay, we need to make sure that the transport relay knows who we are. That thing is, when you bought Office 365, you're paying for a service, so we're not going to give out media candidates willy-nilly. We're just going to give them only to people who paid for our service. So we need a credential to authenticate. Then when establishing the call, and this happens for each and every single call, we will do a candidate discovery and exchange. We'll do connectivity checks, and we'll do a candidate promotion based on the most likely candidate that we should be using. So once we do the credential exchange, and then for every call, it's discovery, exchange, connectivity, and promotion. As far as relay credentials, as soon as we sign in, we tell you, hey, you're going to need credentials. The service helps you to get them. The credentials are being created, and through signaling, you get those credentials. This is important because this is often confused with encryption. It's not encryption, it's just authentication. I'll show you a little bit about the difference between those two in the upcoming slides. So for Teams, it's very simple. The service will provide you the credentials. You will never talk directly to the trap. Because we do level 400, we go a little bit deeper, but as far as all our customers are concerned, the trap doesn't exist. They'll never see it. They'll never talk to it. The client never talks to it. It's just a service. So what happens? When we sign in, we tell the service, hey, we're here. The service says, that's fantastic. Let me get you some credentials. The service talks to the trap. Trap generates credentials. Trap gives them back to the service, and the service tells us. That's how it works. When you connect to a relay, you connect to either 3478 or 443, and from there, you'll be redirected to the actual IP, the actual transport relay that you'll be using to get a consistent connectivity. You will keep a connection over 3478, and during the setup of calls, you might get additional ports for additional media. The candidate list will only have the UDP candidates in the candidate list, and we know that if there's a UDP candidate, there's a corresponding TCP. We're smart. We don't need to say, hey, if we can go to 3479 on this specific IP address on UDP, we know, oh, then we can also use TCP. Every workload has its own specific port on the relay from 3478 up to 3481. So how does this address discovery work? So first of all, we have an IP address. It's on our NIC. We know this, right? So our client starts up and knows, oh, this A, that's my IP address, I'll add that to my list. What we then do, we then talk to the media relay over 3478, and the media relay says, oh, this external, we call this the reflexive IP, this external IP address with this corresponding port, that's where you can find me. That's where you can tell the other party that this is where they can connect to. So that's number C. While we're doing that, we're also saying, oh, by the way, I've seen that your specific external IP address is B. So now we know the internal IP address, we know the external IP address, and we know the external reflexive IP address. So we're already on our way. We also want to know the TCP addresses. Well, that's easy. We go through the same spiel to at least know that the ports are open. It is, and the relay is telling us, sure, you can also do TCP. Reflexive is E, and your external IP address is D. Now, it's important to understand here that, this is using stun. We're getting all these candidates, and we're getting all these ports, but we don't know if we can connect there yet. Right? So we're just learning about them. This is the first step. We're just learning about this. So we now know which ones are available to us. We don't know if they work. So now we want to connect. So we're placing the call. So we're doing this invite. We've done the connectivity checks. We know our internal IP address. We know the external IP address. We know all of this. By now, we've also figured out that we're behind the net. We know that there are a bunch of different IP addresses. So we get a preference for a certain connectivity. We know that we're both not on the same network. So we're saying, hey, if we're not on the same network, by default, we'll use the reflexive UDP address of the relay. That's just the default because we know that will have the most chance of success. As you can see, the other party has done the same thing, but instead of using A to E, they've used V to Z. So in our invite, using signaling, we tell them, hey, this is our preferred candidate. These are all the other candidates that you can connect to us. The other party is very gracious, and they say, oh, we also have some candidates. Look, we've got V to Z. And Y is our preferred candidate. During this process, we immediately try to connect to Y, and we do that so we can establish early media. And we want to have early media, so early media is the part before you pick up. We try to establish an audio channel, and the reason behind that is that, let's say you were playing with your phone, and hey, it's ringing, I immediately pick up and I say, hello, it's Cornel. But because we're still negotiating, you wouldn't hear the hello. You wouldn't hear the first portion. So we need to have audio before you actually have audio. So during the session progress, we're already establishing early media. I get an OK back that I've received everything. I'm happy that the early media is established. And I'm saying, well, I still like this Y. At this point, there's one portion missing. At this point, we send back and tell them, well, we agree with what you've done. We agree with the candidates. We can connect to the other candidates. We can set up an audio channel. So everybody's happy with this check. So what we've done here, just to summarize, is I've used stun turn to establish my internal and external and reflexive IP addresses, so my candidates. The other party has done that too, and throughout signaling, we've exchanged that information. We're probing those ports. We can see if we can connect. If we can connect, we tell them, OK, this seems to be working, and we will be having the conversation on these specific ports. So what about media encryption? Because we haven't done any media encryption. Well, we have. So during the initial authentication to our transport relay, we've gotten MRES credentials from the trap. You see how this gets confusing really quick? So we're not using a media relay, but we've still got MRES credentials. So the trap has given us MRES credentials throughout our initial sign-in. The only thing that does is when we talk to the transport relay, it allows us to request that reflexive IP address. It allows us to talk to it. doesn't encrypt anything. As soon as we set up the call in our invites, we also exchange an encryption key. So that's how both parties know about the encryption key. They know how to encrypt the data. They don't use the MRES credentials for that. So what do we do during the connectivity checks? We've gotten the candidate pairs. We know how we would like to connect, but we don't know if it'll work. So during the connectivity checks, we actually check if the UDP and TCP port pairings, if we can connect to them. So most likely, the local IP address of the other party, we can't connect to that. We'd love to, we can't. It's usually NAT, firewall, stuff like that. We know that our relay can actually bridge between IPv4 and IPv6. It's pretty cool. The nice thing about a transport relay is, if I'm using a proxy and I cannot use UDP and I go with TCP to my transport relay, but the other party can use UDP, the relay is smart enough to bridge between TCP and UDP. So only a part of the way will be impacted. The stump packets are sent between the port pairs in orders to ensure that it's always the same order of checks. So we do internal, we do external UDP, external TCP. The packet response indicates the connectivity, so that's how we find out, using stun, that's how we find out if we can connect to the port, because UDP is connectionless, so we need a back and forth reply to at least know if we can connect. And we stop check when a candidate pair has bidirectional connectivity. And the reason we stop checks is because bidirectional connectivity means we've got a direct connection, there's nothing in the way, we're super happy here. Bidirectional connectivity means that we don't need to relay. We get a direct connectivity, life is great. So how do we promote them? We now know which candidates actually have connectivity, which candidates will work. We'll then use IPv4 before IPv6. We'll use UDP before TCP and direct before relay. That's the logic that's hard-coded in our client. You can't influence that. At the end of our connectivity, we will do a re-invite with just one candidate in the session description protocol so that we both agree on this is the IP address that you need to connect on, this is the port. The confirmation for that from the other side also says, yay, I agree. And at that point, the media is on the, and so while this says the optional validated path, it's on the best path possible between those two clients. If you've blocked everything and we now do TCP between media relays and TCP between the client and the media relay, it's not really optimal, but it's the best we can get. So TCP versus UDP. We've talked a little bit about this. Why don't we really like TCP? So TCP is fantastic when I'm trying to surf the web, because if I'm missing something, it'll automatically retry and get the packet again. Each package needs to be acknowledge that I have it, or else they'll keep on sending the package. Any lost packets are resent. For audio or video, I don't care. I just want all the stuff as quickly as possible. And if I lose something along the way, I have some mechanisms to cope with that. You've probably heard that when you were talking to someone and they were suddenly sounding like a robot. That's a codec trying to repair for lost packets. We'd rather do the little robot voice than delay a conversation for 1, 2, 3 seconds, because we are waiting for the TCP retransmits. So we really don't like TCP, we want UDP. Real-time communication, we want packets quickly. If we lose them, we don't care, we can cope with that. So let's take a little look at some of the call flows. So for one-on-one calls with teams, what you have, so we have our relay servers. They can be the same, maybe they're using different ones, doesn't really matter, the mechanism is the same. So we have two Teams clients. The first thing they do, establish 3478 UDP to the relay server. Now, if we can make the call directly, that's awesome, let's do that. If that doesn't work, what we can do is the Teams client will use the other party's transport relay, because that's what in the other party's session description protocol, right? They use their own transport relay. So we use their transport relay on port 3478 up to 3481, depending on the audio that we use. And maybe that's bidirectional. Maybe I can send audio back and forth. Maybe I can send audio direct, in a direct connectivity from A to B, and from B to A has to go over the media relay. This all works. Perhaps we both need to use a media relay, and we can't do bidirectional. Still works. Worst case scenario, we can't talk to each other at all, and we can't even do any bidirectional. In that case, the two transport relays will talk to each other over port 3478. And that actually doesn't have, we just piggyback over the existing connection. We don't need to set up new connections into the network. So transport relays can talk to each other as well. What if they talk to the service? A lot simpler. Why do we have only one transport relay? Because we know the service can always talk to the transport relay. We don't need to do any piggybacking or going back and forth between the service. We know that our service can talk to our transport relays because those ports are opened. We own that network, so we kind of took care of that. So the Teams client once again connects to 3478 UDP. The service connects directly to the audio ports that the client needs, so 3479 up to 3481, and everything's fine. If the Teams client can connect directly to the service, why not? Let's talk directly to the service. Own relay, always 3478. So some of the ports that we're using, we've got some high ports for incoming audio on the Teams client itself. So we've been talking about the 3478 up to 3481 on the relay and on the service. When it comes to incoming audio, the Teams client, yeah, we call this the high port range, 50,000 up to 5080 from the top of my mind. This is well documented in our Office 365 IP address range, so you can look that up. As far as the service ports for our transport relays, it's always 443 TCP and 3478 UDP up to 3481 UDP. So when opening up your firewall for Teams, port 80, port 443 TCP, 3478 up to 3481 UDP. I know it's super annoying that I keep reminding you of those ports. The average customer right now, if you go into CQD, there's a special report on TCP calls. It's scary how many customers don't open these ports and have all their calls running on TCP, and then quality is bad. Yeah, quality is going to be bad. So do's and don'ts. Yes, direct connectivity. Don't put stuff in between. We have very concrete and direct guidance. If you're going to connect to Office 365, don't put stuff in between. Packet inspectors, proxies, let them connect correctly. Use bypass on those firewalls, those proxies, things like that. Use local internet breakouts. Use UDP. It'll vastly improve your media quality. TCP might be required for whatever reason you have in your company. Try to get exceptions, because it will make it worse. We do have the Office 365 URLs and IP ranges. We try not to change them, but there will be updates. Right now, the whole internet, we're moving into IPv6. This has implications. What we're trying to do, and honestly, when I talk about changes, the changes that we're making is usually reducing the IP ranges. We're trying to use less and less public IPs because no one likes to configure 10,000 IP addresses to open up a bunch of ports. So we're really trying to shrink this down. There's an RSS feed you can subscribe to, so any changes will come directly to you. Hey, and there we go again. Verify that those UDP ports are open. Some tools and troubleshooting. Bad news for those that liked UC KPI logs and stuff like that. They don't exist with Teams. I had about 15 slides about how we could troubleshoot Teams and how you could get logs. And I talked to Thomas, and he said, you can't talk about that because it's not supported. So no logs for you. That's essentially right now the message. We are working on making that more accessible so you can get some logs. It's difficult right now. So for now, there are no logs for Teams. There are some other tools. So we have the call quality dashboard. We talked a little bit about this on Wednesday. This now has a way to do quality of experience, and it will do things like show me all the TCP calls, so you can verify which network segments haven't been properly configured. There's some practical guidance for this on aka.ms/myadvisor. So I'll go quickly through the myadvisor one, the CQD one. So you get some of the modality reports in CQD, like on media and transport, so you can see a lot of the calls that were going out on TCP or UDP. We show you these reports, how many calls you had. You can also do sub-reports here to look at the quality. So for example, in audio, you can see that I had about 400,000 calls on TCP, 300,000 on UDP. This would be an excellent customer to talk to and investigate, hey, why do you have more calls on TCP than UDP? So that's a tool here. It doesn't actually say subnet 1, 2, and 3. That's simply to obfuscate some of the data that we have. But you can actually see which segments are using a lot of TCP or UDP. As you can see, this will help you drill down into network segments that might be improperly configured. There is a Skype for Business network assessment tool. This applies to Team, and it tests the network quality. So what I can show you, who's used the network assessment tool? I did. Keep your hand high if you like the tool. There we go. So I built something, and we'll talk about that in our in the upcoming session. So I've built this together with Jason, our bearded magician, and I'll hope I can release this in a week. It's a PowerShell GUI for the network assessment tool, and you can just, it's a single line of PowerShell code that you need to run on your client. Then you get this. It auto-installs the network assessment tool. It auto checks if everything is right, if you have internet connectivity, if everything is happy to actually do any of these connectivity checks. And as soon as you click the big green start button, what it does is it runs the connectivity checks in the back, it runs the media quality tests in the back, it parses the results and gives you the results immediately. So because I have 2 minutes left, what I'll do, I'll go back to the presentation, and then we'll take a look at the results here. You have to trust me that this runs in the backend, so keep watching me, nothing in my sleeves, I'm not touching the PC. So this keeps running for a little bit, and I'll show you that. So we have this networking tool. It'll be available soon via a blog post. I'll show you the results in about 30 seconds. It will also check actually if the device connected to the PC is a Teams or Skype for Business certified device. So this is a great tool to have your end users run to see if their PC meets the requirements, if the network actually works. Just a PowerShell GUI over the existing tool. So resources in summary. So we have some, I leave this in here. There are some places you can go to get these, the training on this, to get the tool, to get some help on this. Today we talked about challenges for media connectivity, how can we find that optimal media path, and how do we identify connectivity issues. And the 3 key takeaways are traffic can be peer-to-peer, leverage local internet breakouts, and open those UDP ports. While we go back to the presentation, please do the evals. At the end of Ignite, all the presenters get those evals, and we read every single comment. And if you say, this was stupid, we won't do it again. It's as simple as that. So the results have finished, as you can see. Connectivity is great. I can connect to all the right UDP and TCP ports. This is happy. Quality isn't great for this network. Who would have thought? And if I go to view results, it'll actually give me the results here. It'll tell me that my packet loss was 0.2%, which is within our spec. Round trip time, 34 within spec. Jitter is over 60 milliseconds, which is outside of our spec. And our packet reorder ratio is 0.4%, which is also outside of our network requirements. Now, your end user is going to say, there was a bunch of red stuff. What do I do with this? What you can do, you can click the report button and you get something you can actually email to your network admin, and now they know when you ran the test and what the results were. So, and with that, it was exactly 0 seconds. They said if I went over 45 minutes, I get in trouble. Exactly 45 minutes. If you have more questions, come up to me. This really was the last slide, no more slides. And next year, Thomas will be back and he'll be doing this with a charming Austrian accent. That's it.